When you think about a traditional woodworker shop, there's a very specific expectation of how things operate.
Right, it's very organized.
Yeah, you have your workbench right in the center of the room, and then covering the walls, you have this massive array of highly specialized tools.
A specific hammer for a specific nail.
Exactly. A Japanese pull saw for delicate cuts, a heavy router for the edges, and when you want to build a simple chair, you have to physically walk over to the wall, grab the exact tool, bring it to the bench, use it, walk back.
Put it away, grab the next one.
You're right.
Yeah.
It is a highly manual, totally disjointed process.
It requires, constant context switching. You end up spending as much time just managing your tools as you do actually shaping the wood.
Exactly. But imagine stepping into a magical workshop where the workbench itself anticipates what you're trying to build.
Okay, I like where this is going.
So you place a piece of raw oak on the table, and the bench instantly surfaces the exact cutting blade you need, right at your fingertips. No walking around, no swapping out tools.
The intelligence is just built directly into the surface you are already working on.
Yes, exactly. And welcome to the Deep Dive. We are so glad you're here joining us today because we are unpacking the latest Google Cloud Platform updates, specifically the late June 2026 releases.
And we're really looking at how they are turning that magical workshop analogy into a reality for developers.
We are, because let's be honest, reading through cloud release notes can sometimes feel like translating a dry technical manual.
Oh, absolutely. It is incredibly easy to get completely lost in the acronyms.
Right. So our mission today is to cut straight through that jargon. We're focusing strictly on what matters to you, the everyday practitioner.
Whether you are just spinning up your very first cloud project or you're, an intermediate developer managing a growing app, we are translating this into plain English.
Yes, and I promise whenever a specific GCP product comes up, we will take a quick second to explain what it actually does in the real world so nobody gets left behind here.
And looking at the stack of updates, the sheer volume of changes across analytics, databases, and infrastructure, it points to a massive architectural shift.
A theme of consolidation.
Exactly. We are moving away from the era where you had to attach a dozen separate bolt-on services just to get AI to function. Google Cloud is aggressively consolidating those capabilities.
They're baking the intelligence directly into the workbench you already use.
Right. And to really understand this shift, you have to look at where all this intelligence actually lives, which is the data itself.
So let's start right there, looking at how you interact with your data warehouses. And to ground us, let's look at BigQuery.
A great place to start.
For anyone newer to the ecosystem, BigQuery is Google's fully managed, serverless enterprise data warehouse. It's the powerhouse you use to analyze just massive amounts of historical data incredibly fast.
And normally you'd set a business intelligence tool on top of it, right?
Yeah, exactly, like Looker, which is the platform you use to build visual dashboards and spot trends.
Right. But traditionally, getting insights out of that setup meant you needed someone fluent in complex SQL.
You had to know exactly how to structure a query to pull the right needles from a massive haystack of data.
But the introduction of what Google is calling the Agentic Data Cloud completely changes that interface.
This is where it gets wild. They're making it so you can use natural language, like just conversational English, to query data lakes and operational databases like BigQuery and Cloud SQL.
You don't necessarily have to write those complex SQL statements anymore just to get basic business answers.
Which is huge. And they have also introduced specialized autonomous agents.
Right. There's a data engineering agent designed to maintain your data pipelines.
And a data science agent that helps suggest features and even generates data notebooks for you.
It significantly lowers the barrier to entry. But what's really interesting is how they are serving the advanced practitioners at the exact same time.
Because developers still want to write code.
Exactly. The developers who do write code are getting a massive upgrade to their workflow with the general availability of BigQuery managed Python user-defined functions.
Or UDFs. So let's translate that for a second. In plain terms, a Python UDF means you can take custom Python logic, including super popular data science libraries like Pandas and NumPy, and run them directly inside your standard SQL queries.
Think about the mechanics of how we used to do this.
This is a headache, right?
A total headache. If a data scientist wanted to run complex Python transformations on data sitting in BigQuery, they had to extract the data, spin up their own containers, manage Docker images.
Handle all the security patching for that environment.
Right, run the Python script and then push the results back. It was an infrastructure nightmare.
So by making this fully managed and serverless, BigQuery just handles all of that execution environment invisibly.
It essentially bridges the gap between your data scientists who live and breathe Python and your data analysts who rely on SQL.
They can finally work in the exact same environment without managing the servers underneath.
And they are taking that embedded intelligence even further with a new feature in preview called the AI.AGG function.
Oh, this one is fascinating. It lets you use natural language instructions directly inside a SQL query to summarize totally unstructured data.
The source material offers a really great practical application for this. Imagine you have a massive database table filled with messy, varied product descriptions written by hundreds of different third-party vendors.
Okay, yeah. Instead of writing a crazy regular expression to try and sort them out, you just use the AI.AGG function.
Right. You tell the AI in conversational English, hey, figure out what broad retail category these products belong in.
And it just processes that text
Mm-hmm.
and spits out a clean, standardized string right into your table.
Exactly.
Okay, wait, hold on. Let me push back on this a bit.
Sure.
If I'm running custom Python libraries directly inside SQL queries, and I am asking a large language model to evaluate and aggregate unstructured text data, isn't that incredibly computationally heavy?
Oh, absolutely it is.
Like, if I run that on a table with 50 million rows, that sounds like a fast track to a massive, unexpected cloud bill.
That is a highly critical point, and it highlights why understanding the underlying architecture is so important for a practitioner.
Right, because it's not magic.
No, not at all. You cannot treat an LLM function the same way you treat a basic SQL addition function. And the source material explicitly addresses this cost and performance concern.
Okay, so what's the workaround?
The best practice here is strict optimization before the AI ever even touches the data.
Meaning you don't just point the AI at the entire database and cross your fingers.
Exactly. The recommended approach is to aggressively pre-filter your data using standard, highly efficient SQL commands.
So using strict where clauses or the limit command to narrow down your dataset to only the exact rows that actually require synthesis.
Right. You use the cheap lightning-fast tool, which is SQL, for the heavy lifting of sorting and filtering.
And then you apply the computationally expensive tool, the AI.AG function, only on the resulting small batch of data.
That is how you manage token costs while still getting the benefit of embedded AI.
Okay, that makes total sense. So building this intelligence directly into your data warehouse is incredible for analyzing the past and understanding trends.
But what happens when your live customer-facing application needs to use that AI in real time?
Yes, that requires a totally different database architecture. We need a database that can handle millions of everyday user transactions without breaking a sweat, but can also run these complex new AI workloads.
Without forcing us to fracture our data into a dozen different specialized systems.
Which brings us to a massive evolution for Cloud Spanner.
This is a huge one.
Yeah. For those unfamiliar, Cloud Spanner is essentially Google's crown jewel of databases. It is a fully managed, massively scalable relational database.
If you are building a global application like an e-commerce platform or a banking app, and you need a database that spans multiple continents, never goes down, and always keeps your data perfectly consistent, Spanner is what you use.
But historically, Spanner was rigidly focused on those relational transactional workloads, writing data quickly and reliably.
Right. The June updates, however, mark Spanner's official transition into a multi-model database engine.
Meaning it doesn't just do rows and columns anymore.
No, it now natively supports relational data, vector data, graph mapping, key value pairs, and full-text search, all inside a single framework.
It even features integrated vector search using Google's scan algorithms, which enables incredibly fast retrieval augmented generation, or ARRAY-J, directly on your live data.
This is the ultimate expression of that consolidation trend we talked about. You don't need a separate vector database for your AI, a separate graph database for relationships, and a separate relational database for user accounts.
Okay, but again, I have to play the skeptic here.
Bring it on.
Usually when software tries to be a Swiss Army knife and do absolutely everything, it gets bloated and ends up doing nothing particularly well.
That's a fair concern.
If I'm running a global checkout system on Spanner, and my marketing team suddenly kicks off a massive, heavy analytical AI graph query on that same database, isn't that going to eat up all the compute power and crash my customer checkouts?
That is the exact architectural collision that traditionally forced developers to build complex, fragile pipelines to copy data from their live database over to a separate analytics database.
To keep them separated.
Exactly. But what is fascinating is how Spanner solves this under the hood using a built-in columnar engine.
Okay, let's break that down for the everyday practitioner, because transactional data, like a user's checkout cart, is usually stored in rows. It's really fast to write a single row.
Right. But analytical queries like finding the average cart size across a million users prefer data stored in columns.
Because it's much faster to read one specific attribute across massive data sets.
Exactly. Doing both at the same time in one place usually causes friction. But Spanner's engine automatically and continuously routes your live, row-based transactional data into columnar replicas in the background.
Oh, wow. So when that heavy analytical query comes in from the marketing team, Spanner is smart enough to route it directly to those columnar replicas.
You got it.
Ah, so the analytical query and the live checkout are reading data that is synchronized, but they aren't fighting for the exact same compute resources.
Yes, exactly. It isolates the workloads at the compute layer while keeping the data unified at the storage layer.
So your transactional performance remains completely unaffected by heavy analytics.
Right, and we see the power of keeping this data unified in the source materials mention of a financial company called Curve.
Oh, yeah, the fraud detection example.
Yeah, Curve originally used BigQuery Graph to map incredibly complex payment networks to detect fraud using graph query language, or GQL.
So basically mapping how money moves between thousands of different accounts to catch bad actors in real time.
Right, because it requires analyzing multi-hop relationships. User A sends money to user B, who shares a device identifier with user C.
Modeling that as property graphs with nodes and edges is computationally intense.
Highly intense. But by adopting these native graph mapping concepts directly into Spanner, developers can now perform that kind of complex relationship mapping and AI searching on their live operational data.
So you don't have to wait for an overnight batch job to move the data to a warehouse to find the fraud. You find it in place.
It's a massive time saver for data engineers. The data stays put, and the database itself just learns new ways to look at it.
But having incredibly smart warehouses and multi-model databases is really only half the equation, right? You still have to physically deploy and host the actual AI models that are talking to these databases.
Right, you need the infrastructure to run the engine at scale. The intelligence has to live somewhere, and it has to be able to handle massive spikes in traffic.
Which naturally leads us to Google Kubernetes Engine, or GKE.
The powerhouse.
Yeah. For context, GKE is a managed environment for deploying, managing, and scaling containerized applications using Kubernetes. Think of it as the ultimate orchestrator.
If you have an application running across hundreds of virtual machines, GKE is the conductor, making sure they all stay healthy, scale up when traffic spikes, and scale down when things are quiet.
It has become the absolute workhorse for modern cloud infrastructure. And deploying AI on GKE is getting significantly more efficient.
It really is. The updates detail a new guide for deploying a remote model context protocol, or MCP, server on GKE using a Python framework called FastMCP.
Which manages traffic securely via the Kubernetes Gateway API.
Exactly. But the update that really changes the game for performance is a collaboration between Google Cloud and Anyscale to scale Serve LLM on GKE.
Yeah, they have introduced a new architecture called direct token streaming, which completely bypasses the traditional ingress router.
And to understand why bypassing the ingress router is such a massive performance boost, we have to look at how large language models actually communicate.
Let's visualize this. Imagine your infrastructure is a busy restaurant.
Okay, I'm hungry. Let's go.
In the traditional setup, every single dish coming out of the kitchen, which in this case represents a tiny data token generated by the AI model, has to be physically carried by one central, increasingly overwhelmed waiter out to the customer.
And that waiter is your ingress router. It acts as a proxy, inspecting headers and terminating security protocols for every single request.
Right. And when you are generating an essay or a block of code, an LLM is streaming thousands of those individual tokens a second.
Having a proxy inspect every single one of those tokens creates a massive bottleneck. The latency just skyrockets.
So what this direct token streaming architecture does is essentially build a window straight from the kitchen to the dining room table.
The chef just hands the food directly to the customer.
Yes. The overwhelmed waiter, the ingress proxy, is bypassed completely.
It is a brilliant architectural optimization. The client makes the initial request through the normal channels, but once the connection is established, the model replicas on GKE stream the generated tokens directly over the network back to the user.
By removing that proxy overhead, the system dramatically reduces latency.
And when you combine that low latency with the ability to deploy remote MCP servers on GKE, the practitioner's workflow totally transforms.
It allows you to transition your AI setup from something that only works locally on a single machine to a highly scalable, stateless AI service that handles thousands of client connections over standard HTTP requests.
You can host your AI securely on GKE, and it can reach out, connect back to BigQuery or Spanner, process the data, and stream the answers back reliably at massive scale.
Okay, but this is where I start getting a little nervous.
Uh-oh. Why is that?
Think about what we are actually building here. We are giving autonomous AI agents access to our core databases. We are letting them execute Python code on our data. We are mapping complex payment graphs for them and scaling them massively on Kubernetes clusters.
Oh, I see where you're going.
How on earth do we keep these agents from going rogue? Like, if a malicious user tricks my AI agent, how do we prevent a catastrophic data leak?
It is the single most pressing question in cloud architecture right now. Because when you deploy autonomous agents, you can no longer rely purely on human-centric security models.
Right. Autonomous agents require autonomous guardrails.
Exactly. Which brings us to the crucial final piece of this puzzle, security and observability.
Let's define two core tools here before we dive in. First, VPC Service Controls, or VPC-SC. Think of this as a highly secure, invisible network perimeter that you draw around your cloud resources to prevent data from ever leaving your approved environment.
And second, cloud monitoring, which is the system that continuously collects metrics, logs, and traces to track the health and activity of your infrastructure.
So Google Cloud has introduced entirely new perimeter guardrail capabilities in VPC-SC that are specifically designed for these non-human autonomous AI agents.
You can now add agent identities directly to your service perimeter ingress and egress rules.
This gives you the power of rapid revocation, right? If an agent acts suspiciously, you cut its network access instantly.
They have even made it so that if you place the Gemini Enterprise Agent platform inside a protected perimeter, it automatically blocks all public internet access to that agent by default.
They are actively acknowledging that the network boundary has to evolve.
Yes.
But let's dig into a real-world scenario. Let's say a bad actor uses a clever prompt injection attack on my customer-facing chatbot.
Okay.
They maliciously trick my AI agent into trying to steal a database of customer emails. Now, the agent is compromised, but technically, that agent still possesses valid IAM credentials. It holds the legitimate digital ID card required to access my BigQuery data.
Right, it's authenticated.
So if the agent is officially allowed to see the data, how does this VTC perimeter actually stop the data from being stolen?
This scenario perfectly illustrates why relying solely on identity and access management IAM is no longer enough and why VPC-SC is critical.
Okay.
IAM checks who is asking for the data. VPC-SC evaluates where the data is trying to go.
The destination of the data packets.
Precisely. Even if that compromised agent uses its valid ID card, successfully queries the database, and pulls the customer emails into its memory, it still has to deliver that data to the attacker.
Right.
The moment that agent attempts to send that data outside your designated virtual perimeter, say, by trying to execute a POST request to an unauthorized external webhook or an unknown third-party IP address, the network infrastructure simply drops the packets.
Wow. So IAM checks the ID at the front door to let you in, but VPC-SC physically locks all the windows so you can't throw anything out to a waiting getaway car.
That's a great way to put it. It blocks data exfiltration at the raw network level, completely ignoring whatever permissions the agent holds.
And this proactive security posture extends into the new tools being released for observability, too.
Yeah, the source material highlights Cloud Network Insights, which uses monitoring points to send continuous bursts of simulated traffic 21/7, constantly testing the performance and security of your network routes.
They also highlight a multi-agent orchestration framework called Mantis.
Oh, Mantis is really cool. It's designed for context-aware repository analysis and self-healing fuzz testing.
Basically, using AI agents to constantly attack and test your own code for vulnerabilities, and then attempting to heal them autonomously.
And when you pair all of this autonomous activity with the new updates to observability analytics, you get an incredibly powerful feedback loop.
Because observability analytics now supports custom SQL-based alerting over your logs and traces.
Which is incredibly practical for the everyday practitioner.
Yeah, if VPC blocks an unauthorized egress attempt from an AI agent, it generates a log. Instead of having to learn a brand new proprietary alerting language to track that, you can just write a simple SQL query.
Like a basic row count threshold.
Right, that runs against your network logs on a continuous schedule. If an anomaly occurs, that scheduled SQL query flags it and instantly pages your engineering team on Slack or PagerDuty.
It consolidates the tooling. You use the SQL you already know to monitor the advanced AI systems you are deploying.
So when we step back and look at this entire stack of updates, we are seeing a massive evolution in what it means to build on Google Cloud.
It really is a completely new paradigm.
We started with the Agentic Data Cloud, opening up BigQuery to natural language and serverless Python execution. Then we watched Spanner evolve into a multi-model powerhouse, isolating compute so it can handle heavy analytical RAG queries without slowing down a live checkout.
And we saw GKE optimize token streaming, bypassing the ingress proxy to deliver answers at lightning speed.
And finally, we explored how VPC Service Controls act as a network-level straitjacket to keep those AI agents from leaking data, while simple SQL alerts keep your team informed.
Google Cloud is systematically lowering the barrier to entry for complex AI operations, but crucially, they are also building the robust safety nets required to actually use it in production.
The workbench is undeniably getting smarter.
It is. But I want to leave you with a thought that builds on this entire architectural shift we've been talking about.
Okay, let's hear it.
We are now deploying frameworks like Mantis to autonomously find and patch security vulnerabilities in our code. We are introducing data engineering agents to autonomously maintain the health of our data pipelines.
They are starting to do the daily maintenance work.
Exactly. And if the AI is now testing the code, fixing the code, and maintaining the pipelines, how long will it be until these agents realize they can just write their own SQL-based alerts and observability analytics?
Oh, wow.
How long until they start dynamically adjusting their own VPC SC network perimeters in real time, responding to threats they independently discover before a human even gets paged on Slack?
That's wild to think about. As a practitioner, your daily role is rapidly shifting from the person who physically builds the pipelines to the person who supervises the AI that builds them.
It's a fundamental shift for the industry. Are you ready for that transition in your own day-to-day work?
It is definitely something to mull over as you architect your next cloud deployment. We hope this deep dive helped clear away some of the technical jargon and gave you a real sense of where this digital workbench is heading.
You don't have to walk around the shop grabbing individual disconnected tools anymore.
No, the intelligence is being handed right to you. Thank you so much for joining us for this conversation, and we highly encourage you to go explore these new tools and test out these concepts on your own architecture. Until next time, keep building.